By the time the 1960s came along, we had a pretty giant collection of subatomic particles that we defined as the subatomic zoo. Now, we knew about the 6 leptons and their respective antiparticles, so we were pretty confident in saying that these were likely fundamental particles, and that, like, once you got to that lepton, you couldn't get further, you couldn't find anything else inside of it. Now, the issue that we had is with the number of hadrons, because the idea was, could we really have hundreds of fundamental particles? So we're going to really hammer down what we mean by a fundamental particle. But before we get to that, we have to talk about the Quark model. We just have to talk about quarks in general. So this was proposed independently with 2 people in 1964 by Murray Gell-Mann and George Zweig. So they kind of did this independent of one another. And what they figured out is that this quark, it has to be a fundamental particle that makes up other matter. And the reason and how they got to this was from deep inelastic scattering experiments done at the SLAC, or the Stanford Linear Accelerator, in, I believe, 1968. And what it showed is that protons, they're not fundamental particles. It's not you get to the proton, there's nothing else in it. What they found is that there's more underneath the surface of the proton. So we kind of have we have some electrons that are being used in this scattering experiment. Now with a proton, we would expect an electron to be attracted towards a proton. And we can kind of see here these 2 electrons here. They're attracted to the proton. Nothing strange. But you'll notice these electrons down here, they're being deflected away. What that's telling people is that, well, if they're being deflected away, there must be some kind of negative charge inside of that proton for that to happen. And this is where we get to the Quark model. So inside a proton, we're going to have 3 quarks. We're going to have 2 quarks that have a positive charge, referred to as up quarks, and we're going to have this 1 quark with a negative charge, referred to as the down quark. So these SLAC experiments, these help show that, well, the proton, there's more to it. So our definition of fundamental particles is something that doesn't have quarks. If it has quarks, we can't call it a fundamental particle. So up to date, we know of 6 quarks and their respective antiquarks. So we have the up and down quarks, the strange and charm quarks, the bottom or the beauty quark, and the top or the truth quark. In Physics 30, the first generation, that's all you need to know about. You need to know about the up and the down quark. If you're an IB, you got to know about the other ones. For Physics 30, if you have to deal with any of these 4 quarks on an exam, they will be described to you in detail, so you don't really have to know anything about them. So we have the up quark, it has a charge of plus 2/3 e. The down quark is going to have a charge of minus 1/3 e. And then the respective antiquarks, so the anti-up antiquark would have a charge of negative 2/3 e, and the anti-down antiquark would have a charge of positive 1/3 e. Now with that, 2 particles that we well know and love, the proton and the neutron, they are made up of quarks, and they're made up of first generation quarks, so they're made up of those up and down quarks. So a proton is made up of 2 up quarks and a down quark, or we might just say UUD. Let's check. Does the quark composition match the charge that we know? Well, we have an up quark of 2/3 e, we have another up quark of 2/3 e, and then we have that down quark of minus 1/3 e. Well, 2/3 plus 2/3 minus 1/3, that is going to equal positive 1 e. That is the charge of a proton, so we're pretty happy with its quark composition. With a neutron, neutron is composed of 1 single up quark and 2 down quarks. So if we look at the composition, it should give us that the total charge here is 0. Well, we have the contribution of our up quark of 2/3 e. We have the negative 1/3 e for the first down quark. We have negative 1/3 e for the second down quark. So 2/3 plus minus 1/3 plus minus 1/3. This is going to give us a charge of 0, which is what we expect. On a diploma, you have to know the composition of quarks in a proton and a neutron. So a proton has 2 up quarks and a down quark. A neutron is going to have 1 up quark and 2 down quarks.